Hi everyone. This is going to be mainly the lecture about the fundamental theorem for line integrals. Especially the goal of this one is clarify the relationship of between the zero curl and conservative vector field and path independence. For a region open and connected region, this conservative vector field and path independence is equivalent. That was introduced in my earlier video, Introduction to the Fundamental Theorem, Introduction to Line Integral, which is basically pencast. But here this one is focused on zero curl, as you see there, and path independence and conservative part. So let me show you the statement of the fundamental theorem for line integrals here. So the first condition is the open region, whether it's connected or not. And we have these continuous partial derivatives, such that first order, such that we have a chain rule. The chain rule allows us to write this complicated, usually more involved calculation is this vector field, a line integral for vector field, simply is like this. Whenever C lies in the region, so A and B must be in the connected region. So whenever you consider this path, it is completely determined by the values of the endpoint, where this F is called potential function relative to the vector field. One clarification I'd like to make here is if you have a potential function, a scalar function that is defined on any type of region, this type of region, which is usually called simply connected region, so there's no hole inside, and this is not simply connected region, it has a hole inside, and this one even has two holes inside. As long as we have the scalar function defined on this region, this type of region or that type of region, it doesn't matter. As long as we have this region and this scalar function is defined everywhere, this phenomenon will hold. So if you go around this and that, the path independent is going to hold. It's, for example, if we're actually looking at scalar function that is undefined around it here, and so that we have to remove it to make sense out of it, and then if you go around, it's still going to have the same exact path integral, so it doesn't still depend on this on the path. So that's what this says. As long as we have a region simply connected or not, this is going to be path independence if we have scalar function defined all the region on R. Okay, so it's not just because it's undefined that we detected some different path integral. So here's a two example. This is typical example that everything is well defined here. F of xy is this scalar function whose gradient vector is going to be 2x, the partial with respect to x, and partial y, so 2x, 2y. And this scalar function is defined everywhere. So however you do this path integral, the line integral of this vector, gradient vector field, is going to be just like this. Let's look at the second example. This f of xy is a scalar function. It is not defined at 0, 0. So if we have to remove this point to make sense out of it. So the region R of this scalar function will be everything in here except the 0, 0. So that is an example of region that is not simply connected. But we do have this scalar function that is defined everywhere here. So its gradient vector field is going to be this one if you differentiate it with respect to x and y. We can have this one. That's a straightforward calculation. And to visualize this nicely, it's kind of, because we have a same scalar factor, you can ignore that. Just to get the direction of this vector field, you can see it's kind of, this is a parallel to negative x comma negative y. So these are kind of behaving just like a gravitational vector field. It's kind of going toward inside like that. So this vector field turns out to be conservative because the entire region we have this nicely well defined, the scalar function, and the vector field is the gradient vector field of that. So for that one, if you do this integral along the path, it's going to be always the same, whether it's going around the 0, 0 or not. So here's the statement. I mean, here's that picture. So here it is. That point 0, 0, if you go around like that, the integral will be exactly the same like this. So I'm not going with the calculation, but some of you might, if you have a misconcept about this type of thing, might have suspicious about this. You actually do the calculation. It's not that bad if you, for example, if you go around the circle, because the way the function looks like, it's going to behave nicely with the circle parameterization. If you actually try that, you will see they're exactly the same. Okay. Again, it's about the understanding the fundamental theorem for line integral that does not require the region to be simply connected. Okay. Okay, so let me review the properties again. So we're about to enter some parts that we want to decide whether it's a conservative vector field or not. So if we have a vector field, we're going to discuss usually these three properties. On a region, all this property, it is relative to this region we're looking at R. They're going to be all open and connected. Let me write that down. So, okay, I wrote that and I forgot to add that part, but it's important. We're going to look at this open and connected region in there. So when we say the vector field is conservative, when there is a scalar function that is all defined on R here, there I circled it so that on R is the important part. This whole thing is relative to this R, such that on that R, everywhere the gradient vector field realizes. So when we say conservative, we don't just say conservative, it's conservative on R. So don't just realize it's conservative, it's always remember this conservative on R. So that's a conservative property. The second property is the path independence. So we've been using this word again, path independence on R. So let me emphasize that. Right there, I circle the path independence on R. It's going to be relative term to that. That means if we have two different paths like the C1 and C and C prime that has the same boundary. The same boundary here means having a same initial and terminal point. Then these two vector fields, these line integral values of this vector field is going to be exactly the same. However you approach start from the end, it's going to be always same. That's the property of the path independence. Third property I call is a curl being 0. This is not so standard that you call this one curl, but just for convenience of this lecture, let me call this curl of these two dimensional vector field is py minus qx, where these are partial derivatives. When this is 0, it's a good sign that it's going to be probably conservative, and that's the idea. So 0 curl, straightforward. This being 0 means py equals qx. You've seen that probably before. Again, this is on R, right? Every property described here is relative to R. When you change this R to something else, it might or might not change. Especially this conservative is very sensitive, and path independence could be sensitive, and the curl 0 is not so sensitive. And that's probably the most confusing part. This curl is just property of the local field. It is not really depending on the shape. It's just about at one point around it we have this property that's satisfied. And that's why it's, there's a gap between these two notions and conservative path independence and curl. This curl condition is just a local. At any point it might have this point. But this is a kind of global property. So let me show you the picture. So this is a property that R is again an open and connected. So right back in, and then we have to add this open and connected part, and we wrote the conservative and path independence. That's actually proven in my earlier lecture in the pencast that the path independence actually implies the conservative, and conservative by fundamental theorem of line integral, it implies a path independence. It's about connecting this one with this condition curl equals 0, which is py equals qx. So wrote it up there, and that's what it means, py equals qx. And it seems like it's not always so. If there is a condition on that R, this itself can be satisfied at point-wise or locally, but there is some global property should be there to go to from here to there. That property is the simply connectedness. So if R is not only open and connected, but if it's simply connected, then this curl being 0 in that region R actually implies a conservative and a path independence. So having this diagram, it really clarifies these kind of confusion you might have had. So I'm showing you the whole piece that it's that okay, we have these directions guaranteed when an R is additionally this simply connected there. So I circle it, and then if we have this nice simply connected property, and we have this one, and these are examples of a region that is not simply connected, and this is not even connected. But this is an example that it's simply connected, but it is kind of complicated shape, but it is still simply connected. There's no hole inside there. So this demonstration part turned out to be a very interesting example. So let's see, it's going to be a demonstration, but in case that we have a curl equals 0 on a not simply connected region, and then you will kind of see that where the problem occurs or where the problem doesn't occur. It's kind of strange. First example, let's take a look at the first example. Okay, here it is. F of xy is given by these components, and as you can see, because x squared plus y squared in there, and this is have to miss that 0 points, and that's the notation we're going to use here. R square hat is going to be entire real numbers and missing just entire xy plane, missing just the center point. That's what that is. So for this case, we are looking at this vector field, and which is defined on a not simply connected region. But in this case, the answer to this one is still conservative. And next example, we're going to see on the same type of region, which is going to be not conservative. But this one is going to be conservative. Let's see. Some of you may not be used to looking at the integral in this way, but you have to be careful a little bit. So I'm approaching it this way so that this method still works for an abstract setting. Because these component functions are given explicitly in rational forms, your antiderivative method, and there is no confusion. But whenever this is given in an abstract form, the following way of approaching an integral is a correct way. So what we have to do is fx, the partial derivative, is this function, and we want to figure out f of xy that satisfies this condition. Of course, we have to integrate this function here. One way to integrate this function is the following: do this in a definite integral, not indefinite integral form, and that's the path you should take for abstract approach. So to do the definite integral, you got to start from somewhere. So I chose a point, any arbitrary point, which was -1, 1 here. Problem is that we have to avoid the 0, 0. And integral we're going to do is we're going to integrate with respect to x. X is horizontal line. If you start from here, -1, 1, if you do the horizontal integral, it's going to look like this. And if you do the integral along the x-axis, and then we're going to be dealing with other points on here. Okay, fix y-coordinate 1 and integrate along the x-axis, and that's where x is. And even you can change the y-coordinate, and over there -1, y, and do the integral just like it's indicated here. So that's what you see over here. We're integrating from -1 to x. So integrating, changing this only x coordinate, or y coordinate here is fixed. So that y coordinate along this entire integral, y coordinate is fixed, and only x coordinate is varying, and I'm using the variable s here. So integrate ds from -1 to x will be integrating in here. So we're even choosing this y different. The problem here is that if you choose your y to be 0 here, so let me go down to there. So if you start from that point -1, 0, there -1, 0, you're going to encounter a problem. When you integrate to the right, you're going to bump into this problem point 0, 0. So that's going to be a little problem. So why don't we restrict it here, and y is greater than 0, and then we don't have to worry about we're safe, right? So if you're doing all this with y greater than 0, and that's going to be great. So in general, and if we're approaching this abstractly, we have to avoid this type of region. One region we're staying in a simply connected region is this one here, to guarantee that you can do this process nicely. Now we're dealing with this specific example which is not simply connected, so in general there's no conclusion. But for this example, we know where the problem is, we can avoid it and see what we can do about it. So y is greater than 0. So this entire integral will be only valid and kind of based on this -1, 1, where we're keeping this y greater than 0, and we're guaranteed that there's no problem with this integral process because we're not going to run into 0, 0. So if you do the calculation, and here you integrate it, and then you get this 1 over x squared plus y squared. You might pause the video and follow these details, but that's what this is. And this is what we end up at, and this is the candidate. With this phi y, of course, is the only part in terms of y. There's no x in it, that's what I mean. So when you integrate, that kind of relative constant kicks in. Okay, that's good. And y greater than 0 is written here, and all the regions that we are allowed to do this part is this upper half plane, right? Because y has to be greater than 0. So that's what we got. And next thing we do is comparing this one with the y part. Okay, here's f of xy, and showing the same stuff. And one more line here. So let's compare this one with the y component of the vector field. So here's fy. So if you differentiate this one with respect to y, then that picks up exactly the part, and this part got to go, and that one is this, and phi y and phi prime y, and this one must be 0. So phi y must be exactly this one. So if these two things are equal to each other, and then that's going to be 0, you're not going to see anything. So don't try to solve this part. So I was a bit interrupted. I'm back. So I'm setting this phi y to be exactly this function on y, so that this part will be 0. So then f of xy is going to be 1 over x squared plus y squared. It happened that this function is defined everywhere. As you can see, this function is defined everywhere except 0, 0, which is our original region. Then formally, if you differentiate x and y, that exactly agrees with the x and y component of the vector field originally there. Right? But if you just push this technique of integrating in different direction, it's going to work too. So let me show you that part. Try to show the whole thing in the. I'm sure it, hope it can fit in okay. So this fy, and then if we have this function part right there, so if we have just take that part right there, then it's going to satisfy all this property up there, up there. That's going to be satisfied, and then this function we're looking at down here is definitely defined at r2 hat. So we found it. But let me try the same technique. Why not starting from elsewhere, like 1, 1, and integrate y first, not negative 1, 1, integrate x first. It'll arrive at similar functions, and that's what we're about to do. Let's start at the 1, 1, and the problem spot right there is 0, 0 is down here. So if you integrate up and down, any point where x is greater than 0, so let's see if I wrote down anywhere. If x is greater than 0, it's not going to have any problem. It's, as long as x is over here, we can integrate along up and down and bump into no problem. So let me show you the formation. So here's how the whole thing looked like. So suppose, forget about what we have discovered after we integrate along the x. Suppose we started from this new point 1, 1 right there, and go left and right as long as x is positive, and located somewhere with a fixed x coordinate and integrate along the y coordinate. So that will be this part here. Okay, y coordinate starts from 1 going to y, and along that path, and x is fixed, so we're treating x as a constant here and integrating along t from 1 to y. And there's a relative constant we have to throw in, and phi x. So if you do the integral method and do the same thing exactly, and it turns out f of xy can be taken like this. And so that's this part here, the kind of vertical strip, has the same exact function. And then if you compare with a different function, if you go across the horizontal, starting from negative 1, 1, and we have 1 over x squared plus y squared, and vertically we have 1 over x squared plus y squared. They perfectly agreed, so we can just take 1 over x squared plus y squared and define everywhere here. If you do the same method, you will discover there's no problem just going across and extending our function from this vertical and horizontal integral method all the way around. So there's no problem with that. So it is actually the answer right here. As you see, that is the potential function of the vector field. So let me show you the problem again. So this is how it started, and then vector field on a not simply connected region, and there is vector field and it turns out it is really the conservative. So not simply connected is not necessarily means it's not conservative. It can be conservative like this one. Next example is going to be a vector field on a not simply connected region, and it is really not a conservative. So this is the example that this vector field is not conservative, so there will not be a scalar function, so that on this entire R2, that's the sensitive part that you have to understand, won't be able to find this scalar function on this R2 such that its gradient vector field is this one. But if you restrict to the smaller than this one, we'll be able to find such f. So again, it's possible to find little f potential function to match this one on the smaller than R2 hat is because they have this curl condition. So partial derivative this one, partial derivative that one is going to be equal to each other. Let me write down the curl condition again. So it's this one, if py, this one with respect to y and that one with respect to x turns out to be equal to each other, but it is not, we don't have this property on simply connected domain, so it's not simply connected domain. So let's, since we have this one, we can find this and potential function in smaller region. So let's do that. So this part is a repeat of exactly what we did. The same thing is that the way the function shows up is slightly different. So like we did before, we started from -1, 1 and integrate along to the right. Again, this y has to be greater than 0. So I put in there so that this line doesn't hit this 0, 0. So for that region, r greater than y greater than 0, we take the antiderivative using carefully doing this integral. It turns out this time the function, and you might pause the video and do this one yourself, and it turns out the function is this one, negative tangent inverse x over y. The antiderivative you have to go through is the trigonometric substitution is a bit more involved, but this is where you arrive at. And it's interesting that we picked up x over y, and then y is in the denominator, so you have to be careful, but we have this condition y greater than 0, so it's okay. So that's how it happens. Next thing we did is this is across the entire upper half region, left and right infinity is taken care of. So next thing we did is that go to the first quadrant and do the same thing vertically this time and see what happens. So I forgot to show this part. It's a summary. The entire across the upper half plane, we have found this function negative tangent inverse x over y. It's well defined, and this is the potential function for the vector field we've shown here. So it is a conservative on R1. So I did in there. Very poor handwriting, but it's convenient. It's conservative on R1. Okay. So let's do that with y. So we should start from some point, not over here. That's going to be outside the range. We have to do this. Take care of this part where x is greater than 0. So x greater than 0. We start from some point like 1, 1 up there, and integrate along vertically. Then you're not going to bump into any problem as long as we have this condition right there. So you start from this x over x squared y squared, which is q part, and then we integrate with respect to y, and it's supposed to be that potential function. So we're integrating with respect to y like that, keeping x as a constant. So go through the same trigonometric substitution. This time you end up at this function. So I circled it there, tangent inverse of y over x. Okay, and this adjusting factor, if you compare this one with fx, and then it turns out it just has to be this factor without this part. So your phi x is going to be positive tangent 1 over x, so this disappears. And this one has x derivative exactly same as x component of the vector field. So we have that. But as you can see, we're trying to put the constant in there, absolute constant, that doesn't depend on x and y, so that to match this whatever we have it before in f1 is because we want to have kind of function that is consistent everywhere. So we have this function negative tangent inverse x over y. So I wrote it there. This function here is valid for across the second quadrant and the first quadrant there. And from the first quadrant to the fourth quadrant, we figured out the slightly different functions, which is this one I wrote, and it's out of the range, so I'm going to move this one slightly up. Okay, now I'm showing everything, and so this is a slightly different function. So this one function and it's slightly different function, but these two functions are related somehow. So here's how. If you look at the y over x in this part here, if you put y over x in the triangle, this whole thing is supposed to be angle theta, whose tangent value is y over x. So that could be this theta down there. But x over y is simply, the other ratio, and so it's going to be tangent of the complementary angles, like pi over 2 minus theta. So if theta is indeed at less than in between 0 and pi over 2, this is actually the relationship. But in other angles, simply is just up to a constant. So this function and that function here looks different, but it's not so much different. They're only up to a constant. So if you want to make these two functions equal to each other, we have to adjust that at this point to 1, 1. This one is the first chosen function, so we stick to that, 1, 1. And so it's valued at that point, f1. This one is a value negative pi over 4. But if you plug in 1, 1 here, you don't get negative pi over 4. You get actually pi over 4. So you have to add appropriate constant to match this one. So that's the next thing I'm showing. So this is the part. So I kind of simplified down here. This is a point, and that's another point that is determined by the very first function, which is this one. We got the second function here. You got to agree this at 1, 1. If you want to extend this as a single function, right? Although we have two different expressions, must agree on this one. So I looked at the tangent inverse of 1, 1. That's the value. You get negative pi over 4. So what should I add it here to c to get this as a negative pi over 4? And c turns out to be pi over 2 because 1 over 1 here, this part is a pi over 4. Right, this is what I wanted to do. I showed too much, but this is what I wanted to show, the pi over 4. So therefore, this whole thing is a pi over 2, such that this worked out like this way. So that makes this f of 2 to be this one, such that this function, and we found out the main portion here, tangent inverse y over x, with this constant, agrees on that part. It's just about 1 point, but it is a theorem that you will see later that if these two functions, f2 and f1, has the same partial derivative everywhere here, which is fx and fy, then it only is differed by a constant. So if you adjust a constant like this, it automatically agrees everywhere. So we extend this as function f1 to the larger domain going around like this. So far on the union of this L-shaped region, the vector field is conservative because we found this scalar function. So we don't stop it, we go around all the way like this, and then we got this one, and this part functions completely determined, matching that point. Why not going across like this? So that's going to be another x integral, but this time y is going to be negative. So I wrote it in there. We're remaining under y negative and going across x, and you do the same thing. It turns out the same function, just like this one before. So here's a negative tangent inverse x over y. So the formula main part is going to be like this, and we have to again match this condition at 1, negative 1, for example. Any point will do, but 1 and 1, and that's always a tangent inverse of 1 or negative 1, so it's something easily we can compute. So if you stick that in there, 1 and negative 1 in here, that should match the earlier function, which is f2. So f2 is here. That formula is tangent x over y over x and plus some c value. I think that was negative pi over 2. Then that determines this value, 1, negative 1. So it should be negative 3 pi over 4 if you stick that one in here. So the key point is that f2 value here, that second function we found, has this negative 3 pi over 4. Therefore, third function we're calculating here must agree with that one. So that's how we're calculating here. So f3 with this portion and the c that we have to figure out, that must agree with this one, which is the function value from the second function. So that's what I wrote it, and that's the value. So we should match that. So it turns out c is negative pi. With that, we get this f3 value, negative 3 pi over 4. So that's the formula right there for f3. Let's circle it there. So that determines everything in here. And then finally, we're just left with this slit right here. And then by vertically integrating this one more time, we're going to close this up. So we can integrate like this one here, and if you stay in that region, but we're going to find a problem with this existing value that is over here. Right, let me show you in this slide, and this is the situation. Let me draw this x and y axis. So I drew in there. That's where x and y axis are. So there's this point that we should avoid, 0, 0. We are in this region where x is less than 0. Okay, so if you start from a point like this, negative 1, negative 1, if you want to integrate vertically because of this condition, y is free, and you can just go across like this, and that's going to be a y integral. So we're doing in this fashion. It turns out the same function, tangent inverse of y over x that we found before, and then we had to adjust this constant. But this region, horizontal region, was completely determined already by f3. So f3, if you plug in negative 1 to f3, you already get this number, so that we don't have any choice about that one. This whole thing, the vertical function we're calculating, must meet that condition to continuously extend. So f4 we're looking for must be in this shape right here. With this condition, negative 5 pi over 4 is equal to the negative 5 pi over 4 when we plug in this negative 1 and negative 1. So that makes this constant right there. So that has to be the case. We don't have any choice because of that condition. So f4 that we're going across here must be in that form for that region. But f4 connects to the second quadrant over there, which is already computed. And that's a problem. So let's look at it here. f4 of negative 1, 1, which is up there, which is in the first quadrant right here, that we're not showing. If you evaluate that function, that formula we are forced to define to match this f3 overlap there, and it gives you negative 7 pi over 4. But if you go back, this is what f4 is giving about the first quadrant point. But if you go back at 1, 1, we have the initial value of pi over 4. Let me show you this. Well, I have to pull out the file, so I'm just going to state that. So if you go back to the very early case, we started from a pi over 4, and doesn't matter what you started with, this keeps increasing as you go around. So it's going to be always end up, decreasing, so always end up at a large gap at the end. So there's no way this technique closes up as you go from third quadrant to the second quadrant like that. So there is a problem if you want to push this conservative property across the horizontal and vertical and things like that. So locally was conservative, and why not? We'll keep pushing it by adjusting the function. Can we close this up so that it's a conservative everywhere except in 0 and 0? And we couldn't do that. And Theorem says that you're not supposed to be able to do that because of path independence failed with that particular vector field. So this is a good example and exercise to think about what happened if we keep using this curl condition, which is 0. This one, the curl of f is being 0. So if you have this one, we know locally is a conservative, not over the entire region like R2 had, but it's locally conservative. Can we push this one all the way around? And sometimes you encounter a problem like this. If path independence fails, it necessarily should fail. So we're almost done. That we're focused on this curl condition, curl being 0, which is py equals to qx. And does this mean that f is a conservative? Well, yes, if it is a simply connected region, but we're going to go through the proof. We're a slightly simpler region, which is a rectangular region, but it has actually all the general flavor. There's no difficulty of extending this one to a simply connected region. So here's a rectangular region proof. So the statement itself actually tells you everything about what the potential function is. It is defined in this way. Okay, if it's a rectangular region, you can horizontally integrate and vertically integrate like this in a certain order. First, if you horizontally integrate, it's supposed to be already f of xy, and this is going to be some adjusting factor to make everything happen correctly. So there's no x is fixed in here. X is completely an a, so it's the initial condition to match up. This is a different function. It's going to start by integrating vertically first and then adjusting the initial condition there. So if you set up like this, it's going to work out everything nicely. So that's one thing. And from the proof of this thing, and you will see where this adjusting term kicks in. So let's focus on this video just to verify that this is the function that we were looking for. Additionally, we're looking at the two different potential function with this same partial derivative condition. So how different can that be? So I'm explaining here, if these two functions have the same partials like this, fx and fy, then you will see, and then it's going to be actually constant, up to a constant on this region. In this case, it happened is exactly equal. So these are what we're going to show, and that's going to be the end of the video. So let's start looking at the first bit of the proof. Alright, first part starts like this. We have the definition of f of xy given above. Then we're going to use the fundamental theorem of calculus to compute the partial derivative with respect to x first. So this is how f of xy look like, and we're differentiating with respect to x, and you can see there's no portion of x in here. So that's going to be 0. So it is a fundamental theorem of calculus that y is a constant, so this is simply pxy. So that's what we're looking at. fx, the partial derivative, is pxy 0. So that satisfies the condition. So that given pq, the components of the vector field, realize it as a partial derivative there. So let's look at the y part. So back to definition again. This time we're differentiating with respect to y. That is solely in terms of y, so that's fundamental theorem of calculus nicely applies, and we can easily differentiate it with respect to y. This one you have to be careful. The order of operation says we're going to integrate first and then we're going to differentiate, because part of the definition is integrating. So we want, of course, that differentiation inside, but you have to understand it's a slightly different order of operation. This is kind of a big deal in the advanced calculus and in linear algebra analysis part, but I've shown this, I justified this one for continuously differentiable version of this p and the scalar function earlier, so I will refer back to our earlier video to justify that we can swap the order of integration and then differential operator integration if they're not the same variable. So let me show you. So here, like I said, the fundamental theorem calculus will make this second part solely in terms of y easily to just qy, but this integral is done for x part and we're differentiating with respect to y. So swapping this one will be convenient, and that's something has to be justified. But if we can do that, and using my earlier result in the video, an earlier video, this will be swapped around, and that's simply py. Right? What do we know about the py? Py is a qx. So that's the curl condition, so that py here can be replaced by qx like this. Then you have x derivative and x integral. They cancel nicely. So the antiderivative of this part as a function of x is a qxy, this x and that, and keeping y in as a constant. You plug in an x and a in there. That's how you calculate the this integral part. All right, that nice switch is there. Once you have that, and see why I have this qay outside so that they cancel nicely, and then becomes just a qxy and then match the second derivative condition. And the rest of the part I will not repeat. The g part goes exactly like this, so it's a good exercise for you to just pause the video and do this one yourself, and how this second piece is there and add it in and kicks in and cancel each other. Again, you have to at some point use this order of operations swapped around like this. From there, we prove that these both partials are the same to P and Q. So fx is P and gx is P, and fy there and gy, they're both P. So these two have the same partial derivative. So this is a statement again, so I'm showing the many portions. So if I define it like this, we have this same partial. But they're not necessarily the same function. We have the same partials, and it turns out they're exactly the same function. But they're often, if we have the same partials, we can conclude that these are up to absolute constant, not necessarily zero. But in this case, two special cases, turns out they're exactly identical functions. Let's prove that part. Proof, in fact, uses the same technique as one variable case. So suppose we have hx and y, which is the partial with respect to x and y is a 0. This is not just at one point, like a critical point. Don't look at this as a critical point. This is happening at every point in the region. That's the condition. So you can say every point is the critical point. Can we conclude that this function on that region R is a constant function? That's what we are about to show. So the proof usually goes like this. Suppose there's 2 points, x1, y1, and x2, y2, on this region, such that these function values are different. Then it's not going to be constant. If we suppose there's such 2 points, and we can deduce a contradiction. So L is going to be this line that passes through these 2 points, x1, y1, and x2, y2, in this region R, which is part of the xy plane. Suppose we parameterize this. The entire line is parameterized. At t equals t1 correspond to the first point. T equals t2 correspond to the second point. Then by mean value theorem, now h is originally a 2-variable function, but suppose we restrict ourselves on this line. So it's going to be h of xy composed with its t parameterization on this line. So we can consider that as 1-variable function after you compose it. Then by mean value theorem, these two values, h2 minus h1 divided by t2 minus t1, that's going to be equal to some special value of the derivative. So I wrote it this way rather than h prime of t. T equals t star, that's a special value. But since these two values, ht2, ht1, are different, this is going to be non-zero value there. So this non-zero part is important. So this value is going to be non-zero. So let's go back to the h as a 2-variable function and see how we can actually, differentiate this one. That's definitely just a chain rule. So by chain rule, differentiating this one as a 2-variable function involves a partial x times dx dt, partial y di dt. But this says we have hx and hy identically 0. That's a part of the condition. Then this is going to be identical to 0. But we have the special point there whose derivative value is non-zero. So that must be non-zero at some point. That contradicts. So that's a typical line from one variable, but it's happening in 2 variable as well. So it contradicts. So this never happens. So while we have supposed up there, it actually never happens. And that's what this proves. Therefore, if you have two functions that are if one function was partial to 0, that must be constant 2-variable functions. So how are we going to apply this one to f and g? It's simple. This is another standard technique. You're going to set this f of xy and g of xy like this. And it's going to be different. So linear operator, the differential operator is linear, so it's going to behave exactly the way we wanted to get this property of hx being 0 and hy being 0 identically on this region R. So we concluded whenever that happened, the function is the constant function on that region. So that's putting it back in there. So we have this result. Let me write that down in the media part. So this function f of f minus g, which is this h function, is constant function. So we claimed a little bit more than just a constant function. It's actually a 0 function, so the fx and gx is exactly equal to each other. So this, I played with the base point a comma b and see what happened if you plug in a comma b in there. Then if you go back to the definition, let me show you again. So this is definition. If you plug in a comma b, a and a makes 0, and b and b, that makes a 0. If you plug in a comma b to the g, then b and a picks up the 0 again. So these functions is 0 values. Therefore, it's a 0, 0 makes it 0. So since this is supposed to be constant function, hx, that constant we have here is 0. So this is identically equal to 0. So I'm going to add it in. So identically equals 0. So that concludes the proof, and some parts that I'd like to explain about the line integrals and conservative vector fields. Thanks.